Thank you. So my talk is about making life easier for people who are developing peephole optimizations, specifically for the LLVM compiler, but these ideas could be applied to any compiler. Is that flickering or is it just in my... Okay. So peephole optimizations are small transformations that occur at the intermediate language level of the compiler. It typically looks at a small number of instructions and rewrites it into another form, which will be smaller or simpler or faster or more efficient. An example being the strength reduction optimization that was mentioned earlier. And LLVM's peephole optimization occurs in a pass called inst-combine. And this contains several hundred individual pattern matches that happen and tell the compiler to rewrite the code into a more efficient way. And these have been written over a course of many years by many different people, and bugs have crept in. This is historically one of the buggier parts of LLVM, according to analyses. And so to address this problem, 2 years ago, I and some others introduced a language called ALIVE. And ALIVE allows you to specify peephole optimizations to use in LLVM. And it has two important properties. The first is that an ALIVE specification can be automatically verified. Our tool will, if you give our tool a ALIVE optimization, it will tell you if that is correct or if it is incorrect. And if it is incorrect, it will give you an example showing you why it is wrong. In addition, an ALIVE specification can be automatically converted into a C++ implementation, which can then be used in the LLVM compiler directly. And let me just go through the structure of an ALIVE optimization. The main thing that the main parts of it are the source, and that is the bit before the arrow. This shows us the specific instructions that we want to optimize. In this example, we have a multiply followed by an unsigned divide. After the arrow, we have the target, and that is another unsigned divide. That is saying we can combine this multiply followed by divide into a single divide. But the part that we are interested in is at the top, and that is the precondition. And the precondition is necessary because optimizations are not always appropriate to apply. There may be that is only valid in certain circumstances and not others. And so the precondition says when it is valid to apply. And I just want to call out here, the C1 and C2 are what we call symbolic constants. And symbolic constants represent values which will be constant in the program which is being optimized, which is to say they will be known to LLVM when LLVM is compiling the program. And so this allows LLVM to make decisions based on them, such as, for example, only applying this optimization when C2 is a multiple of C1. And then as well, you can compute new values with them. For example, in the target, we're going to create a new constant, which is C2 divided by C1. And that is how we're able to combine this multiply and divide into a single divide. Now, writing preconditions can be difficult, and it can be a tedious, error-prone process. And to demonstrate this, I'll tell you the story of an optimization that was proposed about 3 years ago on the LLVM mailing list. And it's not too important what this does. It was a developer had found a case that he was able to make more efficient that showed up frequently in his benchmarks and proposed it to the mailing list. And one of our colleagues, Nuno Lopez, saw this and entered this into ALIVE, which was under development at the time. And ALIVE told him that this optimization is not correct. And here is an example. Here are some values for the input variables, which show that the original program would have computed true, and the target program, the optimized program, would compute false. So that's clearly undesirable. We don't want your optimization to change the meaning of your program. And Nuno reported this to the developer, and the developer said, oh, there's some additional conditions. C1 and C2 both have to be greater than C3. And so Nuno took these, and he put these into ALIVE, and it turns out it's still not right. This precondition is still not strong enough. So there was some further discussion, and eventually they realized, oh, also the two ranges that we're comparing can't overlap, and the upper bounds and the lower bounds have to differ by a single bit. And so we ended up with this considerably more detailed precondition. And, oh, I've hit cancel. Wait, what happened? Nope. Let me just restart. Oh, we're back. This works. This precondition, with this precondition, the optimization is now valid. And so we say this precondition is strong enough. And so that long saga ended. This optimization ended up into LLVM, and it is being used today. But we might have some questions about this. Is this optimization too strong? Are there some valid cases where this optimization could be applied that this precondition disallows? And the answer turns out to be yes. Also, it's a very complicated precondition. There are 6 clauses in here. And a typical number of clauses for a precondition in LLVM that we have observed is 0 or 1. So 6 is a bit of an outlier. And actually, when I was rereading the thread that discussed this, I realized you could have phrased the preconditions that they stated in this form, which uses only 5 clauses and is exactly equivalent. So yes, this is a bit more complicated than it needs to be. And so the takeaway here is that finding a good precondition is difficult, or can be difficult. It can be tedious and error-prone. And so the question we ask is, can we make this easier? How can we automate this process so that developers don't need to spend their precious time trying to work out the best preconditions for their optimizations? And so we have developed ALIVE-INFER. And so ALIVE-INFER is a method for finding a precondition given an optimization specified in ALIVE. And it's a data-driven process. So we start out by generating examples that we can use in order to tell the cases where it is valid from the cases where it is not correct. But ALIVE optimizations don't correspond to specific concrete programs. They correspond to a set of concrete programs, and those programs may have different types. So this complicates the definition of what an example is. But once we have these examples, we then find a precondition which is true for the positive examples and false for the negative examples. And we do this in 2 steps. First, we learn a set of predicates that we can use to try to distinguish the positive and negative examples. And then we assemble these predicates into an expression, or a full precondition, or rather just a precondition, which distinguishes the positive and negative examples. Well, we actually can infer 2 different kinds of preconditions, which we call full preconditions and partial preconditions. And a full precondition accepts all of the positive examples and rejects all of the negative examples. And that's the strongest precondition, or the weakest precondition, actually, that you would want, which makes it still valid. But sometimes that's not what you want. That may create a complicated precondition. So we also can generate partial preconditions. And partial preconditions still reject all of the negative examples, but they may also reject some, but not all of the positive examples. And in doing this, they try to make the precondition simpler. In both cases, though, once we have generated a precondition, we verify that precondition, or rather, we verify the optimization with that precondition and determine whether or not that optimization is actually correct for all possible inputs. And it works pretty well. We've tried it out on LLVM. We've tried it with the optimizations that are present in LLVM that we had previously translated into ALIVE. And we are able to infer preconditions for those. And we also tried them with some additional optimizations that have been found by other tools. And we were able to infer preconditions in many of those cases as well. So let's walk through how this works. We start out with the example generator. And so let's specify exactly what an example is. So here we have an optimization, the one that I showed you before. And here, for example, are 3 code fragments where this optimization might apply. And what we see is that they are all structurally very similar to the source of our optimization, because that is how we designed the language. But where they differ are in the specific values for the symbolic constants and the types for the operations. And so that then forms the basis of our examples. Each example consists of an assignment of types and then specific values for all of the symbolic constants. And those values must correspond to the types. Once we have an example, we then classify it as positive or negative. And again, you'll recall from the previous slide that there are some free variables, even in these concrete examples, x, for example. So when we classify an optimization, we have to, when we classify an example, we have to say whether the optimization is correct or for the code fragment corresponding to that optimization for all possible evaluations we might give to the free variables or runtime variables, which represent values that will not be known at compile time, but will be obviously known when the program is being run. If the optimization is a refinement, given that for that particular example, meaning that the source and the target compute the same value, or the source is undefined, in which case the target can do anything, then it is a positive example. Otherwise, the example is negative. We use two methods for generating, or actually several methods for generating examples, and the two most important are random selection and using the solver. So random selection works by choosing a type assignment, a feasible type assignment that meets the type constraints in the optimization, and then randomly selecting values for each of the symbolic constants, which fall within those types. And then once we have these values, we then classify the examples either positive or negative. And this is pretty fast because we don't have a lot of free variables. So we can just pass it off to the SMT solver, and it'll give us an answer pretty quickly. The problem here is that we might get unlucky. We might only get positive examples, or we might only get negative examples. So to avoid that occurring, we also use as a backup the full SMT solver. And we essentially pass our refinement conditions directly to the SMT solver and say, hey, give me an example which is positive or negative. And the reason we don't use this exclusively is that it's a lot slower. For positive examples, we're going to have an embedded quantifier, which slows down the solver considerably. And we just have more variables in general. Once we have examples, we then go on and learn a set of predicates, which will be useful to distinguish them. And so the scheme that we use here, where we separate learning into two stages of learning predicates and then learning a precondition using them, is inspired by the Predicate Inference engine, which was presented here at PLDI last year. And the process here of finding a predicate rather, is to first we take a sample of our examples, a small sample. We used 15, but that is tunable. And then we enumerate predicates until we find one which separates the positive and negative examples. And the enumeration process is pretty interesting, but I don't have time to go into it. But the key points are we only enumerate type-correct predicates, and we try to avoid producing predicates that fall into an equivalence class. So A plus B is the same as B plus A, so we don't need to generate both of them. Once we have found a predicate which separates the examples in our sample, we then see how it behaves on all of the examples in our complete set. And in particular, we have to make sure that it is defined for all of the positive examples. And that is because we allow predicates to be partially defined. In particular, we want to be able to have the precondition C1 mod C2 equal to 0, and modulus is not defined if C2 is equal to 0. So but we still want to be able to generate that. So we have to allow for predicates which are partially defined. That is to say, for some inputs, they will be undefined. However, we don't ever want our precondition to be undefined. And that's because the precondition is going to be evaluated by the compiler when it is testing whether or not to apply the optimization. And if the compiler divides by 0, it's probably going to crash, and that's probably going to make your users unhappy. More seriously, SMT does not define division by 0 for bit vector arithmetic, which is the theory that we are using. And that means that your SMT solver is free to interpret that in multiple ways. And we actually had a situation where we were doing cross-checking of the verification conditions that ALIVE produced and comparing how it behaved with CVC4 and Z3, and we found that they disagreed about whether certain optimizations were valid. And that caused us a lot of alarm until we understood that it was because we were implicitly dividing by 0 in our optimization. So the method we use here is we just assume that any example which would cause undefined behavior in our precondition has been filtered out by a meta precondition which occurred earlier. And we can, after we are done, we can go and infer that rather easily. But as a consequence of this, if a predicate is undefined for a positive example, then we can't use it because that example will get filtered out. So let me show you a quick demonstration. Here's our optimization from before. And so I'm not here all day. We'll just pick 10 examples. And to keep it simple, we'll say they're all 4-bit arithmetic. And let's say our sample size is 6. About 5 minutes left. So we'll select a sample here, and then we will begin enumerating predicates. So our first predicate we get is C1 equal to 0, and we see this is true for one of the examples in our sample, but it's false for all the others. So this is not useful. So we'll try a few more, and I'm skipping ahead a bit. But now, all of our positive examples, C2 is not a power of 0, but in all of our positive and negative examples, it is. So this is a good candidate. So now we see how it behaves on all of our examples. And this allows us to divide our examples into 2 groups. Those where the predicate is true and those where it is false. And what we see here is that both of these groups contain a mixture of positive and negative examples. So this is not enough yet to produce a precondition. So we'll pick one of these groups, and then we will take a sample from it. And there's only 5 of them, so we'll just take all of them. And then we go and we learn another precondition, or another predicate. And here we go. So all of our positive examples, C2 is a multiple of C1. And in our negative examples, C2 is not a multiple of C1, or the modulus operation is undefined. And that's fine because it's a negative example. So we'll choose that, and we'll add it to our set of predicates that we've learned, and we will observe its behavior on all of our examples. And now we can divide our examples into 6 groups based on how they behave with our 2 predicates. And what we see is that every group, we have 2 groups that contain only positive examples and 4 groups that contain only negative examples. And that means we can go ahead and learn a full precondition because our predicates that we've learned are sufficient to divide the positive examples from the negative examples. So when we enter the formula learner, we have a set of predicates and we have examples we want to accept or reject. And we could just say, we could just look at the 2 groups that only accepted positive examples, for example, and just derive a precondition directly based off of those. For example, this precondition here. But we don't do that because this produces terrible preconditions, as you can see. So instead, we use a method that produces preconditions in conjunctive normal form. And the idea here is we're going to take clauses of predicates, which are disjunct. And we're going to start with very simple ones containing only one predicate, so a predicate or its negation. And we're going to see, of those, which are the ones that accept all of the positive examples, and of those, is every negative example rejected by at least one predicate, or by at least one clause? And if so, we're done. And if not, we add larger clauses. And we keep adding larger clauses until we have every negative example is rejected by at least one clause. I'm going to have to rush, so for more details, see the paper. And that's great, but that's good for finding a full precondition. But there's some cases where we're going to want to create a precondition that rejects some positive examples. And there are 2 reasons we might want to do that. We might want to create a more concise precondition, in which case we can do that by rejecting some positive examples. But we also might want to generate a precondition before we've fully separated all of the examples, just because we want to get something to the user quickly. And then, once we've done that, we can then continue and try to find a better precondition later. So in either of these cases, we use a weighted Boolean learner. And this is very similar to the full Boolean learner, which generated a precondition on the previous slide, except that now, instead of picking larger clauses and adding them to our set of clauses to consider, we start taking some of the clauses that rejected positive examples and considering those. And we try to minimize the number of positive examples that we reject, but we still need to be able to reject all of the negative examples. And again, for more details, please see the paper. Now, once we've got our precondition, either full or partial, we have to verify it. And we do 2 verification steps. First, we want to see for any precondition, does this make the optimization correct? And so here we use essentially the refinement condition, or the correctness conditions for ALIVE. We say, for all evaluations of the constants and the runtime values, where the precondition holds is the optimization or refinement. If there are cases where it does not, then these are new negative examples, and we can go back and learn more predicates. If we've developed a partial precondition, no, a full precondition, I was right the first time. If we found a full precondition, we also want to make sure, is it complete? Does it accept every possible positive example? And so here we're saying, are there any assignments of the constants where the optimization is correct that our precondition rejects? And if there are, then these are new positive examples. And we add these to our set of examples and go back to predicate learning and find another precondition. So we tried this with 174 optimizations that we derived from LLVM's insta-combined pass. And for each one, we asked ALIVE-INFER to do what it could within 1,000 seconds. And in 164 of these cases, we were able to infer a precondition. And in 133 cases, we inferred the most general precondition, one that accepted every positive example. And in 73 of those cases, the precondition that we found was more general than the one that was in LLVM. And here are two of the optimizations from LLVM. We have the original precondition in bold. And you can see that both of these, we reject many of the optimizations. The one on the left, for example, only accepted 8 of the 251 positive examples that we found for it. These are the preconditions that ALIVE-INFER generated. And we can see the one on the left is very good. This precondition is better than the original one in every way. The other one is kind of questionable, whether or not you would prefer that. But we were able to find it. We wanted to make sure that we weren't just limited to what LLVM already could do. So we took some patterns for LLVM that were generated by a super optimizer called Souper. And this generates programs above, which can be turned into very simple forms, which you can see after the arrow. But this program only works for this optimization only works for this particular program with these particular values for the constants. So it's not very useful for a compiler. So we tried to see if we could generalize it. So we took each of the concrete constants in the original pattern and replaced them with symbolic constants, and then asked ALIVE-INFER to infer a precondition. And it was successful in this case. So this new optimization is considerably more general than the one that Souper originally had inferred. And we were able to do this for 51 cases of the Souper examples that have been posted online by John Reger. So to summarize, ALIVE-INFER is a method for inferring preconditions for LLVM Peephole optimizations. It is successful and is able to generalize optimizations generated by super optimizers. More generally, this method of data-driven predicate learning is useful and feasible for finding in preconditions for Peephole optimizations, even outside its original application for finding loop invariants. And LLVM developers can use ALIVE-INFER today to help them, to assist them in creating optimizations with correct preconditions. The code is available online, and I invite you to check it out. Thank you.
I wonder if you could say something about the effects on status flags and branching, how you handle that.
I'm sorry?
Effects on flags in the processor and also on branching, how you handle that.
Well, LLVM's Peephole optimizer does not handle control flow. It only does individual bits of code that don't include branches. And I think were you asking about flags?
Right.
So ALIVE is designed to understand the flags. You're talking about no signed rep, no unsigned rep, stuff like that? Yes. ALIVE understands all of that. So that will determine whether or not the optimization is valid or invalid for a particular example. But it is not necessary in this particular example. There is a method for inferring flags, but that is separate from this method.
John Criswell, University of Rochester. Nice work.
Thank you.
One question I have is whether the new preconditions that you found allowed additional optimization opportunities in real programs? And if so, what speedups did you observe?
We did not. We did not try it out in LLVM on concrete programs. Our experiments, or rather, our observation was that in most of the cases where we were able to generalize a precondition, those additional cases had already been handled by earlier optimizations within InstaCombine. We did make some proposals to LLVM for a few cases where we found a generalized precondition where we thought it would be advantageous, but we were not able to do any timing experiments prior to this conference.
Okay, thank you.
So I guess you can do the speed up programs with better preconditions, or you can find bugs. Two things.
Yes, if you have a buggy optimization, we can make it correct. And if you have an optimization that doesn't get applied as often as it might be, we can help make it more applicable.
Given the number of examples that are needed, right, for positive, could you also approach catch conflicts between the examples? So if you give if one of the examples was wrong, let's say there are 50 examples and one of those positive examples conflicts with some other positive example.
Conflicts in what manner? I'm not sure.
It was a wrong example.
Wrong in what way?
Okay, I can do this.
Okay.
Okay, let's sorry, one final question.
May I ask you your future work or vision of this work? So does it make sense to totally replace all the existing Peephole optimization to machine generated code?
Does it make sense? In the cases where the machine generated code, ALIVE does not currently cover 100% of all the optimizations in InstaCombine, so it would not be feasible to replace all of InstaCombine with code generated by ALIVE. ALIVE can generate, for the cases where ALIVE can generate code, our paper 2 years ago actually compared the performance of LLVM using machine generated code and the current InstaCombine code, and we found they were roughly comparable. I believe, my personal conjecture is that because ALIVE gives you a higher level look at the optimizations that you are going to be performing, that you would be able to take advantage of that and structure the optimizer in a way to be more efficient than LLVM, but we have not explored that.